Greetings everyone, welcome to the first video on this channel. This is a physics series and an introduction to NYP physics, which is based specifically for grade 9 and 10 students. This is going to be a sort of revision guide where we go over basically the content that is covered throughout the course, mainly the core topics really, and we'll also go over test questions and some ideas which we have, and some tips, and essentially a sort of study guide for students who are in grade 9 and 10. Of course, it's NYP, but it's useful for all curriculums. We just used NYP to basically kind of organize our videos, and this is basically a collaboration between myself and one of my friends, and we're both in high school, so we're very excited to bring to you this series, and let's start. So, just to go over what we're going to go over in this series, as I mentioned, it's going to be a revision guide, but we're going to be going off of the physics syllabus in NYP for grade 9 and 10. We will also be diving further ahead into math and chemistry further ahead as this channel progresses, but we're really starting off with this right now. And we're going to go through all the core topics ranging from forces, energy, thermal physics, electricity, astrophysics, and everything else which comes in the syllabus. So we're going to go through lessons as well as practice questions, as well as some tips and guides which we have, which are based on our experiences, on our mistakes, so that you can learn from them, as well as our strengths and how you can add them to your skill set as well. So we're going to have explanations as well as sample test questions, which will be included in dedicated videos. They are useful for all curriculums, and I think that's very important to know. We are using the NYP physics syllabus, but really this is great for any syllabus, regardless of which curriculum you're doing, whether it's IGCSE or ICSE or Cambridge. The content is still largely the same, even though the way that they're delivered might vary. So, and also remember to leave a comment if you have any questions. My friend and I are more than happy to answer any doubt you might have. And we really look forward to interacting with all of you guys and hopefully help you out. So, without any further ado, let's start on our first video and our first topic, which is going to be based on measurement. So hopefully by the end of this video you'll learn or revise, depending on when you're watching this video, measuring data, as well as fundamental and derived SI units, graphs, scalar versus vector quantities, as well as magnitudes of scale. So how do we measure things? As many of you might know, being able to measure things correctly is essential for any good scientist, whether you're doing experiments or verifying results. So how do we ensure our measurements are accurate and precise? And how do we make sure we use the right units and write our answers in the most effective way? So if you see in the on the left side of the slide, you'll see written in blue are a variety of different values in different units, which are used to measure different kinds of things. You have temperature, you have time, you have currency, you have volume, you have mass, all of these different kinds of things. And if you look on the left, you have a picture of a Formula One race board, which shows you lap times, which are given to a very precise degree, to 3 decimal places. And so how is that important, and how is that benefiting Formula One? So yeah, we're going to have a look at all of that. So I think the first important thing which we need to know when we're measuring something is how many significant figures we calculate something to, or how many decimal places we round something to. I'm sure most of you by now would know rounding, so I won't be going over that specifically. But let's say we look at this example here. We have a sort of line stretching from A, B, C, D to E. Let's suppose they're all points on a road indicating houses. And so we have house A to house E, which is a distance of exactly 58.3697 kilometers. Very precise, I know. Very exact. Now, a lot of times you're going to have questions where you're going to be asked to give your answer to a specific amount of precision. It can be to certain significant figures or decimal places. And as you can see here, we have some examples of those. If a question asks you to give an answer to one significant figure, what you're going to do is you're going to look at the very first number on that value and look at the number next to it, and if that number, which is 8 over here, is 5 or greater, then you'll round the entire number up. And in case you are not very sure what a significant figure is, a significant figure is basically a number that tells you exactly how much, which differentiates a value from another. So as you can see, I have 58.3697. Each single number over here is a significant figure because it makes that number unique. Let me give you an example. Let's say I took this number and I put a bunch of zeros before the 5. So I had 0 here, I had a 0 here, I had a 0 here, I had a 0 here, and I just had a bunch of infinite zeros. Would those be considered significant figures? If you answered no, then that would be right. Why is that? The reason is because the zeros that are before it don't actually change the number itself, right? If I put 2 zeros before it, it would still be 58.3697 kilometers. It wouldn't change. Similarly, if I put a lot of zeros after this 7 over here, so I had 369700000 recurring forever, those wouldn't be considered significant figures because they would not change the actual value of this number, right? Let's say what I did was I put a 0 somewhere in the middle. Let's say I had 58.30697. Right here I put a 0. Would that 0 be considered a significant figure? In this case, interestingly, it would be. The reason is because 58.3697 is different from 58.30697 because you've essentially changed the value of the number, right? 369 is different from 3069. And so because of that, if we have a significant figure which is between the integers, right, between this value, we have to consider it as a significant figure because it is changing the value of the rest of the numbers. So I hope that helped. Anyway, so one significant figure should be fairly simple. We have 5, our first significant figure, then we take 8. We see that 8 is greater than 5, so we round it up, round this 5 up to 6, and the answer is 60. Obviously, it says one significant figure, but we still write the 0 because we can't just write 6. If we just write 6, then the number is equivalent to something else. 6 is not 60. So if we're left of the decimal point, we always still want to include the zeros beyond the significant figure point. Then let's say 3 significant figures. Now what's going to happen? It's pretty simple as well. We go 1, 2, 3. So this is our third significant figure, which is 3. And we look at the number right of it. We see that this number is greater than 5. And so what we'll do is we'll round the 4 up, and it'll become 58.4. Let's say we have to do 5 significant figures. Now this is where it gets a little tricky. Because if we count to the 5th significant figure, say 1, 2, 3, 4, 5, we get 9, right? And now we look at the number next to it, which is 7. We round it up, and it becomes 370 because we round the 69 up to a 70, right? And this is where many students might go wrong. What they'll do is they'll see, okay, 58.37, and that's it. Because anyway, what's the point of putting a 0 there? So in their final answer, they'll write the answer as 58.37. If you do that, you're going to lose a mark. And the reason for that is because if a question asks you to say to 5 significant figures, you must include the 5th figure, even if it's a 0. even if it doesn't change the value of a number, when the question asks you to give the fifth significant figure, you must do it. Why? Because if we wrote 58.37, it would still be the same number, but then the person reading it might think that we haven't accounted for that zero, we haven't considered it. If we write 370, then the examiner knows that yes, we considered that significant figure and we realized that it would be a zero and not any other number. And that's why it's so important. Then you have one decimal place. It's different, obviously, from one significant figure because instead of starting at the first number, you start at the first number after the decimal point, which is 3. And so this ends up being the same as our third significant figure answer, which is 58.4 kilometers. Sometimes you'll be asked to give measurements in alternate units. I know this isn't related to significant figures, but you still need to ensure that you give answers to the appropriate amount of significant figures asked. If they don't ask you to give it to a specific amount of significant figures, your best option is giving the full answer. So as you can see, 58.3697 kilometers. 1 kilometer is 1,000 meters, which hopefully most of you should know. And so what I do is I multiply this by 1,000. You can either stick it into the calculator if you want, so take this number, multiply it by 1,000. But what I like to do is just shift the decimal point 1, 2, 3 places, because 1,000 is 10 to the power 3. So it becomes 58,369.7 meters. Simple. And then finally, multiplying or dividing significant figures. This is very important as well, because this is where a lot of students make silly mistakes. Let's say we have a number 6.84 times 7.3. A lot of students will just stick into their calculator and they'll get 49.932 and write that as their answer. That is incorrect. The reason is because when a number is given to you as 7.3, you assume that you're not exactly sure what comes after that 3. It could be that the number is between 7.25 or 7.34 but has been rounded, right? And so because of that, you do not know exactly what comes afterwards. So what happens is when we're giving our answer, we look at our the numbers that we plugged in before. We look at the number with the fewest amount of significant figures, which as you can see here is underlined, and that number is 7.3, right? And we count how many decimal places the answer has been given to, and we take that number and write our answer with the same amount of decimal places. So over here you can see 7.3 is the number which is least precise, right? It's only been given to one decimal place. And so because of that, we also give our answer to one decimal place only, because we do not know what the answer would be had this number been given more precisely, right? We do not know if it's exactly 7.3 or if it's more or slightly less. And so we write that. And that's where we enter precision versus accuracy. Simply put, precision is the number of significant figures given for a value. So this is exactly how many decimal places you give, right? How many significant figures. If your number is exact, if it's exactly what you wanted to say, then that will be considered precise. For example, 47.5943 centimeters is more precise than 48 centimeters. Why? Because you gave more decimal places. You gave 4 decimal places. Here, there's none. So you have more significant figures, and so it's more precise. Meanwhile, accuracy is how close your recorded value is to the actual real-life value. For example, the acceleration due to gravity on Earth is 9.8 meters per second squared, but you record this to be 10 meters per second squared. Now, 10 in this case would be more accurate than 9.158, but less precise. Why is that? The reason is because when we talk about accuracy, we're talking about how close you are to the right value or the real life value. In the case of 10 meters per second squared, our error is 0.2, right? Because the answer is 9.8 and we gave 0.2. Well, not the answer, but our experiment data gave us 10 instead of 9.8. So we were off by 0.2. If we look at 9.158, we were off by more than 0.6, right? Let's round this up to 9.2. then we're off by more than 0.6. So even though we gave it to more decimal places, our answer was had a higher percentage error than 9.8. So because of that, our recorded value is further away from the actual real life value, our target value, and because of that, we're inaccurate. So what I want you to do now is look at this at the bottom of the slide. You'll see 4 dartboards with 5 darts thrown at each one, and what you'll see is you have a different spread on each. And what I want you to do is, based on where the darts have landed, I want you to tell me if it displays accurate, precise, one or the other, or neither. Right? So if something is both accurate and precise, write that down. If something is neither, write that down. If something is only accurate, write that down. If something is only precise, write that down. Pause the video, take your time, and once you're done, we'll resume.